Presentation of our conference, Professor Dr. Ersh Mary will be with us with the presentations Origins of Life lecture. The stage is yours.
Good. Good, and then we should put this maybe on the Let's, well, if it works, well, it's better like this. All right, can you hear me? Okay, greetings to everybody again, and I want to express my gratitude once again to the organizers for this absolutely lovely meeting. And I also have to say that I feel very much honored because Madame Kence is in the audience, and I am extremely glad that I can speak in her presence. Now, please, if you know how life originated, please raise your hand. Well, I don't see any hand, including the hand of the speaker, right? So you could say, all right, that's fine, that was the talk, all right, goodbye, let's have the party. However, despite the fact that we don't know, I think now we know it much better what we don't understand. That's, by any standard, is an increase in information, right? It makes a huge difference whether you say, I have no idea, or if you ask specific questions. And I'm going to convince you that there are specific questions that nowadays you can ask about the origin of life. Also, at the beginning, I have to tell you something which comes from the late Albert Eschenmoser, who was a very famous organic chemist. He said two things: that the best minds of organic chemistry should go to the origin of life field. And the second thing that he said was, we will never know how it happened, but in the future, we can agree on a possible scenario how it could have happened, and then the job is over. Okay, we are not there yet, but that's our aim. Obviously, we would not like to explain the origin of humans from chemicals directly. We would like to explain the origin of cells. But there are two types of cell, and the eukaryotic cell is enormously complex. Right? This is not what we want to explain, because the eukaryotic cell originates from bacteria. Bacteria have this size and this complexity that you see here in these cell organelles. So we should go to something like bacteria, and arguably these are the simplest living systems on the earth. Now you could mention viruses, but then to use one terminology, they are not autonomous, and actually I don't think they are alive, but that's a big debate. But definitely they are not autonomous living beings. Cells are, bacterial cells are, but there is a snag. Bacterial cells also still very complex. The biggest hurdle here is the genetic code. The genetic code is a very hard problem, and we know it's a result of evolution, right? So we should look at something which looks like a bacterial cell, but doesn't have a genetic code. This will be our aim. Also, I would like to remind ourselves that we are firmly in the realm of the Darwinian approach. So we would like to explain how the earliest replicators originated that have satisfied those criteria. And once you have those criteria, then you can say that, all right, so evolution can be launched. And if you are lucky, you can also explain how molecular replicators ganged up to form something like a primitive cell. That will be our more specific aim in this lecture. I'm going to have two slides with equations, altogether two slides. I apologize for this. Also, I know very well what Stephen Hawking said, that according to his experience, every line of equation cuts the remaining audience in half. Right? So I don't want to lose the audience, but it's actually very important because it's not widely appreciated. So what is, from the dynamical point of view, at the heart of dynamical evolution and replicator evolution in general? So now we are in the realm of chemistry, because this is a molecule A that eats something and produces two molecules of A, and this is the waste. Now, A stands for an autocatalyst. This is what the chemists call them. An autocatalyst is catalyzing its own formation. If you take it away from this equation, nothing will happen. So if the concentration of A is X and you keep the concentration of the substrate that it is eating constant, then of course you will have exponential growth, expressed like this. Now, simple exponential growth, you can solve analytically the differential equation. And the differential equation for this one looks like this. There are two variants here. X1 is one type of replicator, and it grows like this. This is the starting concentration. You know, this is the solution. Exponential growth. Here is the time that elapses, and this is the kinetic rate constant of this process here. And this is another one, right? It's also an exponentially growing replicator, but the kinetic rate constants can be different. In effect, the fitnesses are different, right? Who wins? I'm not putting any constraint on this system. I just want to see how the relative concentration change, you know? So that's the relative concentration, and that's the point. It's also exponential, right? So both replicators go to infinity if there is food ad libitum, but the relative concentrations also have an exponential relationship. And if K1 is bigger than K2, then the relative concentration of X1 goes to infinity as well. Not only its absolute, but also the relative. That's the origin of natural selection mathematically. Okay? There is no other constraint, only the relative concentration. It's good to bear this in mind. Okay. Obviously, life, both epistemologically and ontologically, is rooted in chemistry. So we have to take that seriously. And you must have heard about the Miller experiments, and Miller wanted to simulate an ancient atmosphere and some lightning, blah, 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 you know, looked like a Hadean type of environment. And he got amino acids and some other organics. Now, there is a problem with the Miller experiments. It's spectacular, but it's not directly relevant, because now we know that the ancient atmosphere was not reducing. So the Miller experiments are not relevant to the origin of life, but other experiments are. So one of the things that people have been thinking for a long time is that it's possible that if you can implement something like a chemical pathway that looks like a biochemical pathway in our context, then the chemical pathway to synthesize something like a nucleotide will be roughly similar to what we have today. I think that we have to throw that away. The ancient chemistry producing life molecules for the origin of life may not have to do anything or not much with contemporary biochemistry. So here is my friend, Professor Sutherland. Now, here is one example that I want to talk about. So you can synthesize ribose. You can synthesize a nucleobase just by chemical methods. And your thought would be, okay, so you can just link those two, and then you have a ribonucleoside here. Not so. That's the problem. If you synthesize both of them, and you expect in a non-enzymatic reaction to produce this end product, it won't. It produces all kinds of things that you don't want. It doesn't work. Now, this guy figured out how he should do it, and look at this. This molecule, has a very little similarity to this one, the end product. And the components are very different here. And out of that, you can actually synthesize without enzymatic aid the molecule that you want, And it's rather selective and reasonably fast. So that's the point I wanted to make about chemical evolution. And by the same logic, he was able to actually demonstrate experimentally a whole zoo of relevant chemicals. One of the consequences of these investigations is that probably we should say goodbye to the one-pot reactions, because the ancient Earth was not a one-pot reaction, right? It was not one pot. there it was geochemically different, you know, niches, as you wish, for the chemical organizations that are emerging. So some materials could have been synthesized here, some here, some here, and so on. Some of them are very likely to have come from comets and asteroids. Just recently, they have looked at the Bennu asteroid. It's full of organic materials, including amino acids and all the nucleobases, for example. So all this comes together, but it's not a one-pot thing. You actually, and if you have a boundary of two things, these are molecular hybrid zones, if you wish, right? Like hybrid zones for organisms. So this is a promising line. Now, of course, what you want to have is chemical organizations. So the most important chemical organizations for life is a chemical cycle. The Krebs cycle, or the other name is the citric acid cycle, is a chemical engine like this. It produces carbon dioxide and activated hydrogen by taking in an activated form of acetic acid. No, it literally works like an engine. And also, if you think about it, it's also a catalyst. The whole cycle is a catalyst. Enzymes are also operating in cycles. By the way, any engine which is dynamic, also in technology, they always operate in cycles. So this is a chemical engine. And the enzymes are superimposed on this. So at every step, there is a little cycle, right, that the enzyme is catalyzing. It's a super cycle, okay? Question is whether you can find organizations like that without enzymes. That's the critical. I just want to show something which is even more than that. So these are the so-called autocatalytic chemical cycles. You saw one reaction of autocatalysis. These are chemical organizations that are autocatalytic. For example, the Calvin cycle that is fixing carbon dioxide in plants and cyanobacteria is actually an autocatalytic chemical cycle, although the biochemists didn't realize that because the drawing was not good. So here it is, right? So I'm omitting the external reactants. So if you start from 3 molecules of phosphoglyceric acid, here are the 3 molecules. After one turn of the cycle, you have 4 molecules. Okay, so it's growing autocatalytically. Here is another one, the reductive citric acid cycle. That operates in some bacteria. It's also autocatalytic, and it fixes carbon dioxide also, right? So this is a kind of a twisted representation of the cycle, right? It operates like this, right? It's like the sign of infinity. But you see, if you start from here, for example, you come to this, and then there is a branching point, and then you have 2 molecules of oxaloacetic acid in that. Again, this is a contemporary cycle. Question is whether you can have something which looks like this, a little bit or a lot, and can do the same without enzymes. That's the question. This guy, Joseph Morin, is desperately working on this problem, and you need catalysis for that. At these points, there are different metal ion catalysts that are supposed to replace the enzymes. It's not closed yet. We don't have a fully operating reductive citric acid cycle, although it would be very cool. But we are not there yet, but you will see another one. By the way, it may not be the good idea, going back to a previous remark, to look for exactly the same cycle without enzymes that is now being catalyzed by enzymes. And here is a theoretical chemistry investigation. So what they did, they actually classified the reactions of the reductive citric acid cycle, and then in silico chemistry has generated several alternatives, but using only the reaction types that you have in the reductive citric acid cycle. And then they pointed out that some of the alternative routes, just from the purely chemical point of view, for example, like energetics, seem to be more likely. So once again, we should not stick to the idea of trying exactly to implement the reductive citric acid cycle, but something related, but still autocatalytic, might be much more promising. But this, what I'm going to show you now, actually works. It's an old one. It was discovered by this gentleman up there called Butlerov. You hear the applause. That's for the autocatalysis. Look at this date here. Now, look at the date, right? Now, of course, he did not know that it was autocatalytic, but what he was demonstrating that there is an autocatalytic formation, spontaneous autocatalytic formation of sugar molecules out of formaldehyde. Formaldehyde has just one carbon atom, 2 hydrogens and 1 oxygen. And now we know the core mechanism. So first there is a very slow reaction. Here is a glycolaldehyde, right? And then glycolaldehyde takes up a molecule of formaldehyde. There is an interconversion. Then another molecule of formaldehyde. There is another interconversion. And da-da-da-da-dum here. That's the autocatalytic step. So it's actually multiplying not like rabbits, because rabbits are sexual, but multiplies like bacteria, but at the chemical level. You don't need enzymes for that. This will be important shortly. And of course, it's much more complex than this one. There are several different lines, and you can see how many different types of other sugar molecules you can synthesize in the foremost reaction. So there's a kind of molecular replication here. What you are lacking in the foremost reaction is inheritance. People were desperately trying to demonstrate that you could have alternatives of the foremost reaction that would be similar to each other, but still in the chemical space, you would like to have more than one clean lines, as a geneticist would call it. You don't, okay? So for inheritance, for the time being, you need something more, but it's actually very nice for metabolism, indeed. Okay, so now we should look at informational replicators, because the foremost reaction is a non-informational replicator. This is the classic work of my friend Günter von Kidrowski from 1986. Here it is. It's a very simple experiment, but somebody has to think about it first. So these are just like pieces of DNA. This is a hexadeoxynucleotide analog, because there is some chemical tweaking here. These are trimers, right, with an activated end. What happens is that these two guys, the trimers, are complementary to the hexamer. You have this configuration, and then these will be in physical proximity, and therefore the templating will catalyze the formation of the covalent bond. And since this is a very short molecule, there's a chance that it spontaneously splits into two and starts the next replication cycle. Indeed, it's a landmark result. It's amazing, right? It's very simple. For the young people, that was 86. He had absolutely no name at the moment. So the paper was rejected by Nature and Science and blah, blah. And then ultimately it was published by Angewandte Chemie. This has opened an incredible research field in chemistry. The synthesis of artificial replicators, non-enzymatic replicators. And actually, if you look at the word replicator today, most of the citations are not in biology, but in chemistry. So that's what I call an impact, right? Here is another rendering of the same principle. And because it can be very short, but it cannot be very long, because then they don't fall apart. That's a problem, of course. That's an unsolved problem. But the same principle can be used for peptide replicators. That was done by Reza Gadiri and later extended by Gonen Ashkenazi. Actually, so these are two peptides, right? Here. Now, peptides have also a surface. And if the surfaces are complementary, just like you have the complementary between the trimer and the hexamer in the von Kidrowski case, there's the possibility of a replicating peptide. And in fact, that's exactly the case. So, for example, look at this replicator here, which actually takes up now two different kinds of building blocks, and then you have an autocatalytic replication. This is actually the von Kidrowski mechanism. You have got one copy and another copy. And it was then found that by tweaking the sequences of the peptides, you can actually enlarge a system to a collectively autocatalytic replicator community. So the principle is this is not restricted to nucleic acids. What is, however, important, you cannot have the same digital information copying as in the case of RNA or DNA, because you have small pieces and amino acids individually don't have a pairing like the Watson-Crick pairing. But still, this is a spectacular result. And the limited heredity is much more than no heredity at all, right? So there is a research line that is working on similar things now. Okay, as Maynard used to remark, in evolution biology, it's always good to do the sums, which means that you have to calculate. And there was this question, I mentioned it yesterday. So Manfred Eigen, the Nobel Prize-winning physical chemist, thought about the problem, okay, if you don't have enzymes, you have a problem with replication accuracy, right? And that can cause nasty problems. So imagine that you have got a genetic sequence, let us say 100 nucleotides long, and you copy it, but you copy it with different rates of mutations. The idea is that there is one sequence, this is the wild type, it is the fittest, and everybody else has lower fitness. You will have a distribution in a mutation selection balance. So at every mutation rate, you actually can have the relative frequency of the different types. The wild type is coming from above because, you know, one is up here. If there is no mutation rate, 0, then of course it's only the wild types. Okay? So you are coming down, and here is a very nasty thing. That's the Eigen error threshold. It's like a phase transition in physics. This is where, under the increased mutation rate, the genetic information melts. It's melting away, despite selection. That's the Eigen limit, and it's a formidable problem. You have to have a genome, right? But with this kind of limit, Eigen calculated, the genome would be something like 1 transfer RNA molecule, and then goodbye. So you have to resolve it. And that just shows mathematically that you can calculate the position of the error threshold, but I don't go into the details. You can find it in several places, and that's a simplification by Maynard. The original Eigen thing is much more complicated, but that's it. So it shows that the length is limited by the mutation rate that you can. Okay, so Eigen thought that, okay, so if these guys individually are below the Eigen threshold, so they can be maintained, then you can make a genome by this coupling. Every member is autocatalytic, and there's a heterocatalytic aid. So superimposed on the replication cycles, there's a heterocatalytic aid. So this is why it was called a hypercycle. This is ecologically stable, but as Maynard Smith found out later, it's unfortunately evolutionarily unstable, because if this parasite is efficient, this arrow is thicker than this one, this parasite is actually going to extinguish the hypercycle, including finally itself, because it depends on the hypercycle. It doesn't prohibit the demise. You have to do something. This is a well-stirred chemical reactor, so something else must happen here, right? So that already gave the rise that compartments are important. You know, that you put these things into molecular bags. And there are several researchers who are working on that. For example, this is a work by the Nobel Prize-winning Jack Szostak, who got the Nobel Prize on the work of telomeres, right? And what he demonstrated was that if you put a small piece of RNA molecule into a mice cell that is built out of fatty acids, then you can actually figure out that the trinucleotide acts in that system as a catalyst. But you have successful catalysis only if you have magnesium and citrate. Citrate, every cell has citrate, and then the reaction goes well. This shows that when you are building these chemical supersystems, the molecules have to be at least compatible with each other, or they have to love each other. That is what affinity means, by the way. That's the ancient word. Good. And then if you fiddle around with compartments, then there are ways to grow them and divide them. Here is one way from the Shostak lab. This is a bit unusual, but happens. This is a vesicle. You add micelles, it grows, it looks like a worm. And if you agitate, that actually helps that they undergo multiple divisions by fragmentation, and you can actually repeat the cycle. So we are getting there. It's much more than we have been dreaming about several decades ago. All right, but we would like to couple systems, right? A bacterium is a coupling between cytoplasm, membrane, and genetic material. Something like this we would like to implement. Here is an old suggestion. Here is a vesicle, and here is the internal chemical topology in abstract ways. So this is an autocatalyst, right? Because after one turn of cycle, there are two types of it. This is the food molecule. This is the waste here, and this is a molecule that can build a membrane like this one. But the membrane will also grow because it will be spontaneously inserted into the vesicle, right? So this was the Ganti's idea, 78, that this should be possible. And that led me later in 2005 or something like that, that I actually formed the concept of infrabiological systems, which are not that completely biological, but already have interesting properties. So if you have this combinatorics between metabolism, boundary, and template, you can have the system doublets, right? And this would be the ultimate goal. But most of the efforts today are actually here, creating system doublets. And this is one. You saw this guy yesterday with the parasite problem. What we actually implemented, this is the foremost reaction again. The foremost reaction is put into little compartments. They are water in oil droplets. It's a microfluidic system. So we actually have something of a life cycle. And you feed the system with formaldehyde. What you will find that the droplets are going to grow because of the autocatalytic dynamics of the foremost reaction. And if you apply shearing forces, the growing droplets will actually split into two. It's an implementation of implementation of the original idea by Ganti. I mean, this is last year, this experimental result. Okay, now we go to the Holy Grail, right? Or the Holy Trinity. That's the, that's a Christian thing, but this is a very holy Trinity because we are not there yet, but it's of enormous importance. This guy, Tibor Ganti, was actually one of my masters in Hungary. He's a chemical engineer by training, but he was always interested in the principles of life, ever since he was a secondary school student. And this is the 74 version of the system that he called chemoton as the basic, as the simplest chemical supersystem that at the same time is a biological minimal system. Right? So it has this autocatalytic metabolic cycle. It produces two important substances, V' and P'. V' is actually taken up by an autocatalytic template reaction, like RNA polymerization. And then, you know, this is the spontaneous membrane formation because it's a membrane forming molecule, just like we saw previously. But now all the three are working together, and all three systems are autocatalytic individually, but the coupled system is also autocatalytic at the level of the whole system. Some people would, Stu Kaufmann would call it a Kantian whole, because Kant, Immanuel Kant, made the point, he didn't know, of course, he couldn't have, he didn't know anything about biochemistry, but he pointed out that there is something remarkable about living organisms, because the different parts gain their meaning and their importance, you know, in synergy with all the others, right? And so it forms a whole. It's a kind of holistic approach, so that you cannot just take away anything, right? And this is exactly what is implemented here. If you take away either of the subsystems, you don't have a biological minimum system anymore. So this is what we would like to implement, and it's going on now. There is an ERC project called ERC Synergy project called Mini Life, and that is what we would like to achieve, because there is considerable success with all the infrabiological systems, the combinatorics I showed, when you take two subsystems together. But now I think the time is ripe to go for something like the triplicate nature of the Gandhi suggestion. And that is the aim. So it would be self-reproducing and capable of hereditary variation also in the chemical domain, without the genetic code and without anything like the protein enzymes. That's the next thing. And that would be, I think, the culmination of a kind of synthetic biology, but it's unusual because this is bottom-up. It's not using existing parts of contemporary organisms. I mean, actually, it's most likely that none of the subsystems will resemble the contemporary subsystems, but it will be alive. Okay, let's see whether this is what this is why actually I would like to have it accomplished. Richard Feynman, the very famous theoretical physicist, made the famous statement, "What I cannot create, I don't understand." So we would like to have a proof of principle. Huh? We want to follow Gandhi's lead, and if it's successful, and we can convince the colleague that it's alive, we have proved the principle. Huh? That's my main aim. I'm a theoretical biologist. This is what I was talking about. That's another way of formulating it. The chemoton shows organizational closure. Stu Kaufmann likes this phrase, but it's the same as a Kantian whole. I was actually explaining that already. And of course, going back to the lecture of yesterday, once you have such compartments that have metabolism genes inside, you also have a satisfactory solution of the eigen problem. That's the stochastic corrector model. So this is something like the chemoton. It has metabolism, it has a membrane, and it has got also replicators inside. But although both types of replicator are necessary for successful compartment growth, they can have differential replication rates within the. And that is something like what people now call intragenomic conflict, but that of the earliest possible kind. What you can demonstrate is that if there is selection for an optimal composition of the compartments, then selection among the compartments can sufficiently oppose the selection within the compartments, which is just internal competition. Otherwise, the system would go down the drain. You can mathematically prove that this is actually a successful solution. So everything seems to fit together, right? At a certain level. So we shall see. I mean, part of it, what I'm telling you, is not, tinned. Obviously you have the concept of tinned food, yeah? So the food is made and then you seal, then you just have to open and eat it. Now, this is not tinned science. This is science in the making, and some of what I'm saying could turn out to be wrong, right? But I'm happy to be wrong if somebody comes with a better suggestion. Okay, so the same kind of organization also solves the eigen problem. And here is some background literature. This one I showed. I showed yesterday as well. There is a Turkish translation of a popular book with John Maynard Smith. But this is much more recent. And it's remarkable because it's written by two groups. One of the groups is very hard-nosed experimental chemists, and the other group is theoretical biologists like me. Okay, and this is in Nature Reviews Chemistry, from self-replication to replicator systems en route to de novo life. It's open access, so it's easy to say, because there, of course, you see a lot of details that I cannot explain in a public lecture like that. It has got a lot of chemistry and many more equations, just to... Maynard Smith used to say, if you cannot stand algebra, keep out of evolutionary biology. It's not completely true, because there were successful people like George Williams or Richard Dawkins who made very important points without mathematics, but it's rare. Okay? That's actually the chemoton symbol. Thank you very much.
We express our gratitude to Professor Örş Setmeri for his contributions. The 18th Aykut Kence Evolution Conference Committee has made a donation to the BIO Scholarship on your behalf, and we would like to present this certificate to you.
Thank you. Thank you very much for your attention. Thank you. Thank you. No questions? No questions. Oh, good. All right. Okay. Thank you very much then. Yeah? And then just can you...
Değerli katılımcılarımız, birazdan kapanış konuşmamız başlayacaktır. Akademik salondaki katılımcılarımız da genel salona gelecektir. Yerlerinizden ayrılmamanızı rica ederiz. Teşekkürler.